Everyone, thank you everyone for joining us today. My name is Mateusz Kubuszok, and today I will talk to you a little bit about why should you care about JVM. In this talk, we will talk about all the details of JVM, how it works, all the internals and intrinsics. I want to just focus on some the most interesting parts that could tell you, okay, I'm a Scala developer. Most of the time, I don't care that I'm working on JVM, but perhaps at some point I should start caring about it. So short about me so that we will have it crossed. So I've been working in Scala for 5 years in different companies, working with different technologies to gather some experience. And over time, I started learning a little bit about both functional programming, some internals of JVM, things about more complicated stuff with functional programming that aren't so as simple as approach. Well, most of my findings I published in my blog, and at some point I also published a small book about JVM, which helped me learn some of the things that I wanted to share with you today. And I also published some small open sources under the namespace Scala.io together with my friend Piotr Krzemiński. We have small successful library Chimney, which is used for automatic conversions between different data types, which is compile time and saved. So that's all about me. So let's get back to what this talk is about. So the plan is first to talk a little bit about JVM, what it is, what is happening underneath that we should actually take care about, and does it even affect us? Most of the time, we want to abstract away from implementations. Cat's effect pushes that even further, but still, sometimes we might care. So this is about what is happening underneath. Then we will talk also a little bit how JVM types differ from Scala types, because there's some huge difference. Scala compilers tries to hide those differences from us, but sometimes they appear, and it is worth understanding where they came from and how they affect us. I'll tell a little bit about threads, not as much as other plugins that making publication about Cat's effects and concurrent programming and safety and stuff. I just want to show why do we care that JVM support threads, which will be very, very short and sweet, I hope. And finally, I mentioned a little bit about the optimization that JVM does for us, because this is also one of the huge aspects why we are using JVM instead of some other platform, and what JVM was picked for development of Scala and what it's taken, because at some point Scala was also targeting some other platforms, but in the long run, we're still on JVM, and other platforms are, well, slowly joining us. But we're not programming on .NET, for instance. So to explain what is JVM, I guess some example might be useful. In general, we might think that JVM is some sort of emulator of non-existing processor that performs some operations written for this processor, and we don't have to think what platform we are targeting, whether it's Windows or Mac, whether it's x86 or some other platform. We just targeting this one non-existing processor, and things should be resolved for us. Obviously, in the real world, it's slightly bit more complicated than that, but that's the basic idea why we are using JVM. And underneath, if you want to understand bytecode, we basically have to understand what that, basically we will be working with some sort of assembly language for JVM. So to see how this assembly language works, let's take a look at some small example. So this is a very simple example. We are having one main function. We're initializing it. We initialize two variables. Then we add them together, and finally we print results. So it's a very simple program. It's very difficult to find something simpler than that, which is still useful. So as an intermediate step, let's try to see how Java would see this example before we translate it into the JVM bytecode. So first thing that we'll notice is that Java sees all of those variables like A, B, and C as of integer type. This is slightly different from int type from Scala, but we'll get to that. We also see that there's some weird things about printing. So first thing we see that is that we are extracting module from predef. Basically, in JVM prefers us to use objects and instances of objects instead of like some global functions and methods and variables. So when we have object in Scala, they are basically defined as a module field within its class, making it kind of a global that we can globally access. But why we need this Scala predef? Basically, print line, which we sometimes use, is a method of Scala predef object. This object is automatically imported by the Scala compiler, so we don't have to do it ourselves, but we can use some flags that would prevent that, and then we would have to manually import scala.predef _ to import all of the features that are for us to use. But by default, we have them imported automatically for us. So here we can see that explicitly that when we are carrying print line, actually we are going to the Scala predef class. We're taking a look at the static field module. From there, we are extracting the singleton instance of Scala predef, which we want to use, and then finally we call print line on it. So already some interesting things are happening. And finally, this C variable, which should store the result of our addition, is kind of wrapped with some integer. This is also something that we'll get to, but so far we should already be understanding what is happening. We have two variables, we are initializing them, and we initialize the third one by adding two of the variables together, and then we're getting some function to print the result. So how would it look like in JVM bytecode if we compile that? Basically, it would look kind of like this. So what we're looking at is some sort of like an assembly language of Java virtual machine. This is the native language that JVM understands. For us, it might look a little bit alien, so we'll work step by step from all of these instructions. We see that a lot of these instructions doesn't take any sort of parameter. At line 7, we see that they start getting some parameters, and when we are calling some methods, then JVM basically stores any sort of references to fields or methods or classes that we call as some sort of constances compiled in the JVM bytecode, and then the bytecode is referring to them through the some number assigned to them by JVM compiler during the compilation. So here we are seeing only some numbers, but happily for us, if we want to preview the bytecode through some tools like JavaP, it tells us what those numbers resolve to what kind of fields or methods. So if we wanted to execute this code, how would it look like? So let's take a sheet of paper and write everything down. So what if let's start with the part when we are adding two variables and put them into the third variable. What JVM would see is that we have, well, those instructions that we execute in consecution. JVM would also remember at which instruction we currently are. It would have some local variables, which would have no names, only numbers. So it's the compiler that maps the names that we are using to those numbers, and internally the bytecode only uses those numbers. And there is also stack. Stack is a way for JVM to basically pass arguments around, some to store the intermediate results. So hardly ever we are working directly on the local variables. We have to move them to stack to be able to use them. And when we have result on stack, we also move the result from stack to variables. And this way, JVM only needs to deal with a limited number of data at once, even though we have like a lot of variables out there. So let's like try to execute this code. So at first we were starting with the iconst1 instruction. What it does is it initializes stack, it pushes in the stack the constant value of integer 1. It's like specialized function, specialization that uses exactly integer type. It's exactly one constant of 1, and it pushes it to the stack. So once we execute that, we have 1 on the stack. We also see that the program counter, which is like tracing where we are at the program execution, how it moves. So it moves to the next instruction. The next instruction is iStore2. So for the first few local variables, JVM also have those specialized methods to storing the top of the stack to the instruction. This basically means that take the integer, which is on the top of the stack, and store it into local variable with number 2. So once we execute it, stack is again empty, and the local variable 2 is initialized with a value of 1. Then we have a very similar to the instruction, the first one. It, as we might guess, it initializes, it pushes to our stack constant value of 2, which is integer. And once we run iStore3, similarly, we should be able to take the value from the top of the stack and put it into the local variable 3. So that's like the first 2 lines of our initial code when we are like initializing variables A and B. So now is the part when we are taking A and B and adding them together. So in order to add them together, well, first we have to load the values to stack again. So the instruction is, first iLoad2 is loading the integer from the second variable to the stack. Then we are loading the integer from the third local variable to the stack. So now we have 2 of them, and we see that when we push things on stack, usually we put them on top of each other. So basically that's the idea of this metaphor, that you always push things on top of one another, and you can only, if you want to access them, you access them in the reverse order in which you push them. So you can always putting the things on top, and when you are taking things, you are taking things from the top. So now we reach the iAdd instruction, which, as we guess, will take those 2 things, combine them, and put it back on the stack, because stack is place where all of this computation happens. And yes, after that, we will see that on the stack, we got the value of 3, the result of our computation, and finally, we would have to store it to the variable. This iStore difference from the previous ones is that it takes an argument, because the specializations are only made for the first few local variables. If we're above the number 3, then we have to add this extra parameter saying, okay, which local variable would we have to initialize. So that's why we have to pass it explicitly here. So far it was simple. It basically showed us that each of those instructions are like very, very simple. We have stack that we are using to hold the intermediate results, and that all the instructions are working on. And that we have local variables that we usually aren't using directly. If we want to use any of those values, we have to move them to the stack so that they will be available to the instructions of the JVM bytecode. So this is where we are right after those 3 first steps. Now we are moving to the part when we are calling this predef module to call some methods. So I decided to show this because right now there are some interesting things happening. It will be on one hand very similar to what was happening so far, but on the other hand, it will be also introducing some new things. First question that we might have is why we cannot pass integer to this printline function. If we take a look at the signature of this function, we will see that it's accepting Java lang object. So is integer not an instance of Java lang object? Well, the answer is no, because JVM makes distinction between basically two kinds of data. One of them is the primitive types, which are basically Boolean values or numbers. They are basically self-contained. They have specializations in bytecode, which works directly on them. They don't have any sort of methods, like in objects method that we could call. They only have like the primitive instructions supplied by JVM. And the other thing is the other type are reference types. So the reference types are things that extend Java-like objects. Even if we don't do this ourselves, Java compiler or Scala compiler will always make sure that whatever we are implementing is extending this object. And so the way that those two works are slightly different. Like, as I said, with primitive types, they don't have methods. They're only like working with the instruction that JVM provided for them. Objects might have methods. So if we want to call something on them, there's a special set of instructions where we would like pass the object, pass the argument, and the JVM would they make a call. And finally, there's also the void type on JVM, which is kind of special because it helps us annotate methods which are not returning any value, as opposed to methods which are returning values. Like on Scala, we're used to the fact that we can always combine every two functions. In Scala, it's not necessarily the case. Like when we have the function returning void and then we have another function taking void, then we will have to have some special case handling if we wanted to combine it into one function, totally different than we have in Scala. So once we know that primitives and reference types are different, we might see how this code executes. So as we said before, first we need to have this instance of the Scala prediff so that we would be able to call the method printline on it. For that, we are calling getStatic method. As I said, JVM prefers us to use instances. Basically, the whole idea about JVM, Java, its design is that we should use objects wherever possible, and primitives are only used in special places for performance. So static calls were kind of discouraged for quite a while. But what's our statics? Well, basically there are they are basically globals. They are methods or fields that aren't attached directly to any method, to any instance. So they could be called from any place that have the right accessors, which basically makes them global. So with this global, we are able to obtain the instance of Scala prediff. And once we call it, the instance of Scala prediff lands on our stack. Then we are loading number 4 because the variable of 4 is the variable C that we wanted to print. And because printline doesn't allows us to basically print integers, it wants us to print objects, we're calling this static method that Scala library provided us to box this into integer. So basically all of this of JVM's primitives have associated wrapper. Java is able to, since I guess version 7 or so is able to box things automatically and unbox them. But basically on the bytecode level, it's taking the primitive and putting it inside nice, warm, cozy objects so that all the methods requiring objects would not complain, because if we pass the primitive, it would complain. So here Scala compilers does the nice things for us. It takes this integer and use this provided method to wrap it into Java-lang integer, and because Java-lang integer is a normal Java object, it extends Java-lang object, so we are able to pass it into print line, which is why we are able to invoke this method on Scala printf instance. So why it's called virtual? It's called virtual because when we have instances, as you might notice, you might have more than one implementation of the same method. You can have this one trait or one interface and have several implementations of it, which means that you have basically need to have the object that you are calling the method on in order to figure out which implementations you are using. And this instruction does exactly that. So when we are running it, it will take the object, which is why we had to put it on stack, use it to resolve what is the implementation. And once it found the implementation, it will go right into this function and initialize all of the arguments so that we will be able to continue and execute the code. And as we executed, in the case of this object, we got empty because println is not returning any value. So the part about making calls was kind of interesting. So let's stop a little bit with them. First thing that we notice is that so far, we always have the situation that we knew in which method we are. In this case, I haven't written that, but we were basically in the main method of the test object. We always know at which instruction we are. Usually this pointer to this instruction, to this exact line that we are at, is called program counter. Then we have the set of local variables. And we also have the operand stack, which stores all of those temporally intermediate results. And all of that is stored inside a frame, so that when we are making a call, from which we probably would return at some point, we would be able to restore the exact state we were before, with the exception that instead of like arguments, we would have to unstack the return value. So when we are making a call, we create a new frame. We'll making JVM aware, okay, which method it is, at which place we are, usually at the beginning of the method. What are the local variables? They can be initialized to the arguments passed to the method. What is the operand stack? I would expect it to be empty at the beginning of the method. So all of that is initialized. If this is method called on an object, so the invoke virtual, you can guess that one of those local variables initialized will be this argument, which we could use to refer to the methods and fields inside the current object. And if it's just like a static call, then we would only have the local variables initialized with the arguments. On the return, the frame is destroyed. We're getting back to the immediate previous frame. We move in the program counter by one instructions, and we change the operand stack so the arguments disappear and the result returned by the function, if there is any, appears there. So this is basically what happens every time we like call method and return from it. And this is quite noticeable if we like keeping, well, trace of it. So that's basically what stack trace is. When we are like from exception and we are fetching stack trace from it, we basically telling JVM to expose to us those information about what was the state of each frame when the exception happened. We can use it to print the order of functions called. We can learn what were the variables set in each of the nested calls. Debuggers use it so that they are able to show us what is actually happened at the moment we stop the debugger. So this is not only something that is like internal detail of the JVM, it's also something that is directly exposed to us, and we can make use of it. And this is quite important because if you ever work with like a concurrent code, like for a while, then you might have seen a lot of stack traces that were pretty difficult to understand if you didn't have any sort of context. Like recent versions of Monix or Cat's Effect or Zio makes it better because they started tracing where some IO response was created. But for a long time, when you got the stack trace, it was only telling you exactly what JVM returned, which is the very stack trace that we are seeing on the screen. There is still some code that is outside Scala, everything that is basically written in Java that relies on it. So it's just something that we should be familiar with if we ever want to like debug Java code, understand what is happening, be aware that we even can use this during debugging or while reading exceptions. So, okay, now that we understood mostly what JVM does like under the hood, we might take a look at some differences between JVM and Scala types. So let us remind a little bit how Scala type hierarchy looks like. We have the top type, any, which is something that is which all of the types like extends. So we might use any sort of type as a type of any. We have bottom type, nothing, which extends all of the type, which basically means that this type is empty because there is no value that is member of both byte, bool, char, any objects I can think of, but still we are able to describe this using type. We have a null type, which extends all of the types that are objects, like normal objects as opposed to numbers or unit. And we have any vals, which if we take a close look, they're basically mapped directly to what are primitives in JVM, as well as unit, which is kind of a type, but not really. So with that, Scala gives us some way of having like a consistent way of composing functions and having no exceptions in type system that we would be able to, that we would have to work around. If we have one function returning unit and another function taking unit, we can combine it. There is like no special handling there. Types are like aligning, so we can combine it. End of story. This is not the case in Java, because as we said before, we have a distinction between primitive types and reference types. So basically all of the primitive types is a type of its own that we cannot combine with anything else. We have objects which have something like a top type, Java-lang objects, but Java-lang object is not an instance of any of primitive types, so we cannot combine them. We have nothing like bottom type, which is quite useful when we want to represent some empty collection of some consumer of, or maybe something that is always failing or never returning. We cannot really use type system of Java to express that. So if we compare it, we can see that the like most noticeable difference, like if we compare them, is what is happening in Scala and eval. If we like compile those types, we can see that Scala compiler does something very interesting. So it's take a look at our context and see if we could use those types as primitives, or if we could use them as, or if we have to use them as objects. And if we can use them as primitives, it compiles the code, the JVM bytecode to use primitives. And if it says that we need to use objects, it compiles JVM bytecodes to use objects. So depending on the context, it would use two distinct JVM types that like cannot be interchanged, which has the immediate impact for us is that we cannot use like, for instance, Scala int for Java-lang integer. Like we cannot replace one with the other. We have to convert them, because when we have Java-like integer, we know we are talking about an object. If we see like that Java is using a primitive, we know it cannot be object. But when we have like Scala integer, for instance, it's up to Scala compiler to decide what it will be in the bytecode. So we cannot really like interchange them. We have to convert them like explicitly. Another thing is that there is Scala little subtype of all references. We cannot do anything like that in JVM because of obvious reasons. When we have any sort of like generalization, once we like approach the generics, we'll see that it doesn't make really sense to use something like that in Java. And there's also like nothing, which is also used to express that we have some subtype of all types, which again doesn't make sense in Java because they're like separate hierarchies for a lot of things. So there's like a little bit more impacts of this distinction with numbers between like JVM and Scala. So when we are working with Java, and we know that Java can box objects, like we saw a moment ago. Like there's like Java lang integer and simply int. So when we are boxing, we could see that basically all of the classes describing numbers have one common supertype, Java lang number. And when we're working with Java libraries, we could see that there are some libraries that relied exactly on it. They want us to provide anything that extends Java lang number, and then they will work with integers or double or big integer or anything like that. While on Scala, we basically don't have any sort of type that extends one common interface. Well, we have common interface of any val, but it doesn't provide us anything meaningful. So instead, we are relying on Scala numeric type class, which would tell us, okay, when you are passing this code and it has a numeric type class, you are able to add those values together or subtract them or whatever. And this is one of those things that you can quite often see, for instance, of Stack Overflow, that people are like surprised that because they got used to be able to add any two numbers, or any two classes which extended Java lang number, and suddenly they've discovered that, okay, their Scala numbers for some reason don't want to work with Java numbers. And why? Supposedly Scala is like on top of JVM, and suddenly it doesn't work. So, well, basically that's the reason. Scala compiler tries to do things for us, but because it needs to be able to decide some things on its own, then we can really assume that Scala primitives and Java primitives are one and the same thing. So that's one of the like huge impacts of how JVM's design has on like Scala design in some corner cases. Another things that when we could see the difference is when like we would like to understand what is happening on JVM is like generics. So when we have, for instance, take a non-empty list and want to extract head. Well, this is like very simple example. We know what we need to expect. If we have an empty list of A, then we need to receive a value of A. And this is very, very simple. But what's this JVM? So when it comes to like generics, there are like two possible approaches. One of them is that any single time we need a generic, we will create a new type and we will create a separate implementation for it. It's called reified types. The problem is that if we want to create some types like dynamically and not in the runtime, and if the compiler won't generate it for us, then we have a problem. And also, if we want to use them in a slightly different way that the creators of the like JVM or whatever VM's type system intended, then we also have a problem. So for this reason, that for instance, .NET is using reified types. In current version, they are not able to use higher kinded types, which we used to rely on it like quite heavily. But we are able to use higher kinded types because Java developers made a different decision when they needed to implement that functionality. So what is happening on JVM is that when we compile code to the JVM bytecode, we forget that anything like the type parameters exist. So when we take a look at the JVM bytecode, it's as if non-empty list didn't have any sort of like type parameter, and instead it will be having the top level type of all of the Java JVM objects, which is Java-lang object, unless we put some like upper bound on this parameter. But if we don't put it, it usually resolves to Java-lang object. So from the JVM point of view, we will be always putting their non-empty list of Java-lang objects, and what will be extracted will always be Java-lang objects. But if we, for instance, pass there a non-empty list of string, and we know that this is a non-empty list of string, then we are expecting whatever we receive will also be string. So what JVM would do, what compiler would make sure that JVM would do is that the moment we pass arguments in, we're kind of forgetting what the type parameters are. And the internals of this method have to be designed in such a way that they do not rely on any assumption about what this type parameter is. Like if we take a look what generics does, they usually are implemented in such a way that we aren't relying about any information what this type parameters do, only that it stays the same in several places. And then once we are returning value from this parametric function or method or class, we're casting it back to the internet type, and on JVM level, it's not a safe operation. It can always fail, but before we compile it, the type system of either Scala or Java or whatever languages targeting JVM, this is where we are making sure that this as a whole is safe. So when we are like using generics, for us it's a safe operation, even though on the bytecode level it's unsafe operations when we are forgetting what kind of type we're using, and then we are casting back the result. So this has like some implications. One of them is that if we try to use a reflection, then basically anything that is parametric, well, basically only sees everything like objects, so it makes things more difficult. Other like consequence is that, as you can see, it can only like take Java-lang object or whatever upper bound we put there. So it cannot take anything like primitive, like integer or bool or whatever. So we always have to box. Scala tries to address it by using the specialize annotation, which lets the Scala compiler to generate a separate implementation in case we are using this very specific type. So if we are using, for instance, int, and we have the specialization for int, then there will be two parallel classes on the output, and the Scala compiler will not, okay, in this case, I will have to use this implementation instead of this generic implementation, and then I won't have to box the values that I'm putting there. Another like consequence of the fact that we have verified generics is that because JVM aren't making any checks that we would have to conform to, we are able to implement whatever type system we want, as long as we like make sure that it won't produce any like faulty results, which is why Scala was able to add higher kind of types there. And those higher kind of types like, well, works because there are like no obstacles on the JVM level. So it's one of the things that actually allows us to get Scala to what it is today. Threads. I won't be talking long about threads. There's a lot of other presentation that digs this topic like much deeper. So what is important for us on JVM is that the way threads works is that we have several concurrent or parallel operations going on, and they all are happening inside one process and sharing one memory. That means that if we have like two threads, they are able to accessing the very same objects. We don't have to figure out the things that people have to do if they are like working with multi-process applications, when they have to somehow like serialize object, push it through inter-project communication protocols, deserialize, and so on. No, here we just, if like another thread was passed the object on the creation, or if it's available globally, they can both use it, which makes a lot of things easier. The creation of the thread is also very simple. Like threads were available in Java since JDK 1.0, which was released apparently at 23rd of January 1996, which is like 24 years ago or even more. So this is like a huge part of the Java history. Like that's one of the most important things why I'm talking about is because it's been in Java since almost the beginning. Which means that a lot of code is embracing this, and this topic is like pretty much recognized and well described, and a lot has been built on top of it, which we all cannot tell about many other languages. Like for instance, C++, I think at version C++ 11 got something called unified memory model. Before that, there was like no common implementation of threads that you could use. In C++, you always have to rely on some platform-specific code. Well, in Java, we could always use the same implementation, which translated to systems threads. So like here, we have like some very simple examples how to create a thread. We basically only have to create an instance of thread and run start of it, and then we are starting a new thread. Like that's as simple as it is. This thread obviously will die immediately after because it doesn't do anything. But yeah, basically that's all we have to do to instance a thread. If we want to make it do anything, we can either pass a runnable instance. Here I used abstract single method to basically define it as a function, or we can override the run method. And that's everything we need to do to create a thread. But because creating a thread might be expensive operation, we would like to make sure that we won't do that very often. So if we have like multi-threaded operations, usually we'll use something like a thread pool. So which basically means that we have like several threads which are like living and waiting for some job to do. And then we are posting some task on the queue, and as soon as one of the threads becomes available, it will like become idle. We'll be able to take the task from the thread pool and start executing it. But because this will be like pretty mundane for us to do manually, this is where a lot of Scala frameworks came in and started wrapping it around and providing us some nice abstraction over it so that we wouldn't have to do this ourselves. So for instance, execution context is basically a Scala-specific wrapper for Java thread pools, which allows us to make use of the thread pools. We can use an implementation that is available, put it inside execution context, and when we are creating a new feature, this feature will make sure to post things to this thread pool and obtain the results when they became available, and maybe then post another task to execute. Well, the details are like depending on the implementation, if it's like a future or Monix task or CatFX.io, or if it's Akka actors or Akka streams. But somewhere on the bottom, basically all of them are using those thread pools to make sure that we are initializing thread once and then reusing them to provide some, to give us this nice async functionality. Most of the time, we don't have to think about it too much. We need to start thinking about it when we need to define our own execution context because our own is, for some reasons, not enough. So most of the time, we don't need to care about it, but sometimes we need to like tune a performance, or if we need to understand why something is not happening, even though we like pass the execution context and things should be okay. So it's worth knowing that what is happening somewhere underneath, that there are like some threads running inside thread pools, and we might be able to take a look at them ourselves. And the last topic that I will also have to skim through, go very, very fast, because almost all the time are optimizations. So basically the idea is that if we think that JVM is only an emulator on existing processor, things would be pretty slow. Like the first version of Java were pretty slow because they were only like interpreting instructions as JVM reached them. So at some point they have to change it because you cannot really do anything if your interpreter is like super slow. So at some point hotspot appeared, and the idea of hotspot was that if we will keep trace of which part of our applications are more used than the other, we would be able to like optimize them just in time. If we know that some part of the code are like heavily used and some of them are like almost not used, then we won't focus on those not used. We won't do anything ahead of time. We only focus when we see which part are like heavily used. So how JVM approaches JVM's hotspot approaches that is that it makes some distinction. So initially everything runs through interpreter. The JVM doesn't make any hotspot doesn't make any sort of effort to figure out how to optimize, what to optimize, anything like that. It just interpret everything and starts counting how many times some method has been called. And once it sees that some method has been called like 150 times, 1,500 times, see, okay, so this is something that is frequently used, so we might start doing something about it. And so here comes the first compilation engine called C1, also known as client compiler. So the idea is that it should be able to compile things fast. So it basically takes the JVM bytecode and turn it into assembly of the platform we are working with to basically use a native code. It doesn't do any sort of profiling, and it doesn't do any sort of aggressive optimizations. It should be fast and dumb. So the only kind of like interesting thing that it does is inlining, and it would inlines usually trivial methods, which are up to six bytes of JVM bytecode. It might do private method inlining and final method inlining because those never changes. They don't have any sort of like polymorphic implementations. We always know that they are something that never change, so we can safely assume that okay, we can inline them without any sort of thing. And when there are like some we can also inline something that is not very big. So by not very big, JVM by default understands 55 bytes of bytecode. This also could be like inlined, and this is mostly everything that JVM client does. It's only like inlines very simple things, obvious things, and compiler to assembly to make things faster. Then once the method has been called 10,000 times, JVM knows, okay, it would actually be beneficial for us to do some more aggressive optimizations, and then profilers comes in, so that JVM knows who called this method, how many times, how many different optimizations are there, things like that. There's like a lot of optimizations that this code can do when the code is something like a pattern matching on the patterns inside the code, and besides on that, depending which kind of code to use. So that's like cut some implementations, remove, replace with something something better. But this has like another limitation, that the code that we are like compiling aggressively can be very big. From what I remember, it's up to 325 bytes of size. So if it's anything bigger than like C2 will just like give up won't even try. Also, like when it's like anything like inlining or things like that, there's also like an upper limit to how much JVM tries to inline things and optimize things. If it's like too much nesting of calls, it will also like give up and just interpret things. So among the things that we can optimize, they're like, well, inlining is like the maybe not necessarily optimization, but a so-called mother of all optimizations. If we call insert method and see, we don't know if some arguments are used or not, if we can remove some branches. But if we inline things, then we have some insights how our values are being used, and maybe there's some like branches that never happen because the function is returning always true, and this true is used in our condition, and so we know the condition is always true, so we can remove some dead code. So inlining is like something that unlocks other optimizations. Loop unrolling is another optimization where JVM might decide, okay, if we want to get through, I don't know, 100 numbers, then instead of like checking every single time if we already exceeded the number 100, we might just go, instead of stepping by 1, we can first step by 3 or by 4. And if we step by 4 and we see that we still below the limit, then we are safe to extract 3 or 4 values, and only after we exceed this counter we can say, okay, so how much values we not use in this loop, last 2 or last 3 or something like that. Sometimes the JVM would also be able to like figure out, okay, in a lot of places we are making null checks, but we see from the usage or from profiler that null level happens, so we can remove the check and remove everything that depends on this null check. We can also exceed it and like remove the dead code if we see that some code will never happen, some code will never be reached because of reasons. We can also remove that. It's also escape analysis. It's like an allocation optimization, and we see that, okay, the objects that we are using, they aren't used anywhere except our method. They aren't like returned or passed over to something that might save them or store them for later use, and they are used only in the current method. And probably instead of allocating them on heap, we can allocate them on stack, which will be faster, easier to delete, and so on. Another optimization might be like the virtualization, like in the code, see, okay, I'm always calling this virtual method and always like checking what is the implementation of this code, and I see that, okay, there's only one possible implementation we can use. It never happens anything else. So we can basically assume that there is like only one implementation, so there is no reason to resolve this method call. We can just assume that this is always this function, and if we are able to assume that, we can basically inline it, and then since we inline it, we can like run all the other optimizations. There's also things like constant folding, where JVM might say, okay, maybe instead of like recalculating those constants being like added or subtracted or multiplied again and again and again, we might just basically cache the result and use it here because it's not going to change. And like a lot of other optimization, like there's like whole page dedicated to optimization that JVM might perform directly on the oracles page, which you can see later on. So if we take a look at like how this does affect us, we can see that basically JVM prefers like short methods because they're easier to inline and compile. JVM prefers not too deep call stack for the same reasons. JVM prefers simple code because this code is like easier to optimize. If we are limiting number of the implementations, it is also like good for us. Like there was an example by Fabio Brazil when he noticed that at some point Scala developers wanted to optimize things and they wanted to make specifications for, I think those were maps of different size. So they made separate implementation for map of one pair, map of 2, of 3, of 4, and map of more than 4 elements, something like that. And for small cases, it worked better than before because you had the specialized code. But in the bigger picture, right now you have like 5 or more implementations. So your JVM cannot assume that, okay, we have only one implementation here, so we cannot inline the code. We cannot unblock the optimization that we would be able to do. So in the long run, we de-optimize code when we thought that we are optimizing it. Which gives us the final like takeaway is that JVM is already doing a lot of optimization for us. So before we start optimizing things ourselves, maybe we should start by like doing benchmarks to seeing if things aren't fast enough, or if our optimizations actually help. Because this is hard, I would like strongly recommend to digging a little bit into like good learning resources about optimizations and stuff. And yeah, this is one of the images that like really shows what things we should avoid. Like in Spring Framework is like very like easy to end up with this kind of call stack. And if we remember that JVM only wants to inline and attempt to optimize for several nested calls, then we can see that basically all of this call stack is never optimized, never compiled. So basically it's interpreted. Also, especially if there is some reflections on the way, which always makes things extra hard for a compiler. So yeah, it's pretty slow. What we want to avoid, we want to have easy to understand, but also easy to comprehend by JVM code. Source of this, like this was published by Peter Thomas some time ago, and this picture is like quite a meme amongst some people. So finally, written the summary. Sooner or later, you're gonna run into some JVM's idiosyncrasies. Like most of the time, we try to avoid them, but every once in a while, we like meet something that basically requires us to have some knowledge of what is happening underneath. Otherwise, we will be like completely lost. So it's better to understand some stuff. So even when we are using like FP libraries like Cat's Effect or Monix or maybe even like Akka, at some point something is going to happen that will force us to understand why they made such a design decision. Like a lot of smart people are trying very hard to make sure that those limits, that JVM's limitations aren't like imposing anything on us, but sometimes it's unavoidable. So it's good to understand when those things came from. And also, like, if you want to optimize a problem, you're better like learn some basics, mostly like how to measure things. Otherwise, you might be optimizing in wrong places or doing something that JVM does already for you. So if you are curious, I gave you a list of sources. Like the biggest list is like everything that Oracle is already publishing about JVM. I think there's everything there, or almost everything. Daniel Spivak also have really nice guests about thread pools and about fast JVM tips. The whole Alexei Shipilev's blog is about different pitfalls of optimizations on what JVM does underneath. So it's also great read. There was great presentation by Fabio Labellas about how fibers work and what is underneath happening in like Cat's Effect in IO to do all those nice stuff that we are relying on and how it translates to those like low-level things. Definitely recommend. And if you are very lazy and you don't want to take a look about the resources, I compile a lot of things in my own book. But it's just a saying, this is nothing that you cannot find anywhere in the web for free, just a compilation of stuff so that you have them in one place. I will publish this presentation later on online, so everyone interested would be able to like find the links there. So are there any questions?
Amazing.